Okay, so welcome to Math341. This is lecture 6. And so what I want to start doing today is going into some of the detailed probability calculations. There is a bug going around the high school that has been brought into my house. So I apologize. This is about the loudest I can talk today. I do like this material. I apologize for not being as enthusiastic today. I am still under covers. Oh, anyways, so what I want to do today is I want to cover a bunch of materials. I want to talk about, one of my favorite problems, trying to calculate trump splits. Out of curiosity, does anybody here play games like Bridge or Whist or Vint? Yeah. Oh, well. Hearts. All right, spades. All right, so you can still use a lot of those calculations for stuff like that. This will lead us to talking about conditional probability. This is Williams College. You are all smart people. I trust that you can read books and go online and you can learn specific facts. I want to talk about how do you determine if something is reasonable. And again, I really want to emphasize sniffing out formulas. This is the skill that you will use after this class. It's the 21st century. You can look up specific facts. We'll talk about inclusion, exclusion. This is a really powerful technique to calculate a lot of probabilities. And the hope is for a lot of calculations that you need to do, you don't need to calculate things exactly. Oftentimes the first correction term is more than enough. I remember in high school chemistry, my AP teacher said heat something for approximately 2.00 minutes. Approximately, right? That's pretty exact, for what we're going to be able to do as human beings in a high school chemistry class. So get a sense of how accurately do you need to understand things. For a lot of the stuff that you're doing, you don't need to know the exact answer. You just need to be pretty close. Inclusion, exclusion is a great way to get close. And depending on where you stop, you can get upper or lower bounds as to what the actual answer is. We'll talk about Bayes' theorem, which allows you to calculate certain probabilities that you want from the probabilities that you know. So in life, you always want to keep track of, at the end of the day, this is what I want, but this is what I can do. So how can I get from this to another? How many of you have seen or heard the old joke about the statistician who always gets a bullseye? Just 1 second. Hello? Okay, thank you. We have somebody in the Zoom waiting room, so let me see if I can get them in. So the way the statistician gets the bullseye is they first shoot, and then they draw the bullseye afterwards, and you get 100% accuracy by doing it like that. A lot of times people do some analysis first, and then they say, well, this is always what I was interested in. So what you really want to be careful about is, what is your goal? What are you trying to do? And if you're honest, you tell everybody ahead of time, this is what we're looking at. In the real world, you do not always have all the information you need. There's another type of issue. In addition to not always having all the information you need, what else often happens in the real world? In addition to having information that in addition to not having the information you need, what else can sometimes happen?
The information you have is incorrect or wrong.
So there's unfortunately that as well, yes. So not all the information you have is correct. So you want to actually double check and make sure, is this reasonable? Is there a typo? Is there something that happened? There's another issue that can happen. You don't always know what you want, but there's another information about the data that you have. Very different than homework problems. Homework problems are nice and concise.
The data is very messy, or there's a spice in the way the data is gathered, where needs to be considered when doing experiments on it.
Yeah, but you're missing something. And it's kind of nice that you're all missing this because you're so used to problems that are so nice. It involves the color red. It's called a red herring. You have information that doesn't matter, that's not needed, that's not useful. It's so nice in standard cookbook problems. We give you exactly what you need and nothing more to solve the problem. And there's no challenge in trying to figure out what's important. Well, in the real world, you don't necessarily know ahead of time what's important and what's not. All right, and then if time permits, we will talk about derangements, which is related to some of the stuff here. All right. So I apologize. I wrote a couple of things just to save some time because I was not sure how long my voice would last. So has everybody at least seen a deck of cards? Right. There are 4 suits: spades, hearts, diamonds, clubs. Each suit goes 2 through 10, and then jack, queen, king, ace. Typically in games like bridge or whist, you might have one special suit, which is trump. Or if you're playing a game like hearts, you might have hearts as the special suit. And you might want to know how are the cards distributed among the different hands. So in a game like bridge, it's 2 people are one team, and the other 2 are the other team. And so if a suit is trump, that's good. You want to have as many of them as possible. And you might want to know how are the remaining trump distributed among the other 2 hands. I know this is being recorded, so this will be a great opportunity to put my mother-in-law on the spot. A couple of days ago, we were playing bridge with her. I opened with a 1 spade bid in bridge. I had 5 spades. My partner bid something. I supported her. And then in a shocking move, my mother-in-law bid 4 spades over my 1 spade. She had 6 spades, which were really good. And she thought her hand was so strong that even with my having 5 spades, it was worth it. It was not worth it. It will reset her. So you want to know how are the spades distributed. And so let's say you and your partner have 8 of the 13 trump cards, and there are 5 that are out. So it's possible that one of the opponents has all 5. And that could be really bad for you because it could take a while to deplete them. It's much better if it's split, say, 2-3-3-2, because then you can get rid of them quickly. So a very natural question to ask is, what's the probability that of the 5 trump that I'm missing, the 5 spades, they're all in one hand? And so I'm going to give you 2 different calculations. What do you notice about the 2 different numbers? Yes? They're not the same. What can you immediately tell me about these calculations? At least one is wrong. Is it possible that they're both wrong? Yeah, I mean, I'm heavily medicated. I might have really screwed things up today. But we know at least one of them is wrong. One way we could figure out which one is right is to try to think carefully as I go through this. What's another way we could try to figure out which one is right? You could simulate. Good. That should be your default go-to. Whenever you have a problem, can I write some code to simulate this? Okay, and I will show you some code in a moment that I'm quite proud of. As I was checking before today's class, I had an oh shit moment when I thought, oh my God, is this code wrong? And it was, no, code is just extremely efficient. Okay, so let's look at the first one. I've got a bunch of products of binomial coefficients. So let me tell the story. The first to choose one is there are 2 opponents. One of them is going to get the 5 cards. I have 2 choose one ways to choose which one gets them. So let's say I choose one of them. And normally in bridge, we use north, south, east, and west for the names. So let's say east is going to be the one that's going to get them. So I have 2 choose one ways to choose which opponent. Then they have to get all 5 of the missing trump. That's 5 choose 5. There are 21 non-spades left. They have to have 13 cards total. That leaves 8 more cards for their hand. That's 21 choose 8. And that finishes East's hand. Now their partner, I have to give them their cards. Well, there's only 13 cards left, and their partner has to get all 13 cards. That's the 13 choose 13. And I now have to divide by all the ways I can form 2 hands of 13. I have 26 choose 13 ways to choose 13 cards for the first person, and then 13 choose 3 for the second. And so when you do that and the dust settles, you get 3.91 approximately, 9/230ths. To just write things out a little bit, I actually just expanded the binomials and I crossed out as much as I could. There's actually a kind of nice story here. So again, whenever you see math, you want to listen to it and ask, what is it telling? This is just multiplying everything out. 21 choose 8, that is going to give me it doesn't want to okay, it wasn't letting me draw. Okay. So if I look at 21 choose 8, that's 21 factorial over 8 factorial. 21 minus 8 is what? 13. And then 26 choose 13 factorial is just going to be 26 factorial over 13 factorial, 13 factorial. Oh, this is great. We can see a 13 factorial is going to cancel. Then the 13 factorial downstairs is going to come upstairs. 21 over 26. That's going to become 26, 25, 24, 23, 22. And then the 21 and onward is going to cancel. That's where these numbers are going to come from. I've arranged them in a good way. 13 26ths. I take my first spade, and maybe I can interpret that as that's the probability the first spade goes to east. There are 26 slots it can go into, 13 belong to east. For the next one, the 12 25ths, there are now 25 spots left. How many of those spots are available for east? 12. And then the next one is now I have 24 slots. So this is a great example of conditional probability. That as the deal progresses, as I keep putting out cards, I'm filling up East's hand. And the probability that East gets another trump, it does seem like that should become smaller the more trump already in its hand. Because I've filled up more things, and now West needs more cards. And so when you do all that, you get 9 230ths. The other way of looking at it is if I look at each trump card, what's the probability that each trump card, is in East's hand? 1/2. So I have two choose one ways of choosing which person gets all the trump. Each card has a 50-50 chance of being in East's hand. So it would just be 1/2 to the 5th. And so when the dust settles, you get 1/16 or about 6.25%. So does either of these approaches seem unreasonable? Yeah.
Well, I think we kind of show that the second approach is unreasonable by the first example where we showed that like after, as someone gets more and more spades, the probability.
Yeah, I was debating whether or not I should explain the 13 over 26, the 12 over 25. This is priming. So the question is that this is where I really wish I had two sections of probability, because I would do the lecture two different ways. If I hadn't primed you, would you have seen that? Or was this now priming you to look at it in a certain way to make this unreasonable?
I mean, definitely 13 over 26, something like that.
As soon as you saw, and again, so much of mathematics is how do you present things. Two of my friends dropped out of college for a year to help a magician set up an institute to debunk psychics. And so when we're not recording, I will share some very interesting stories about how you can arrange things to get people to look at things in certain ways. I agree with you that the first one seems far more compelling to me than the second. That this seems to be making the mistake that as you keep getting cards in East's hand, they're still going to have a 50% chance for each additional one. And so here is the computer code. I wrote it in Mathematica. It's not that many lines of code. And so again, I am writing code tailored for a very specific problem. I only care, I have 26 cards, and I care about 5 special cards going in one hand. So C goes from 1 to num bad. Num bad for us is going to be 5. And I'm going to create a deck of 26 cards, and I'm going to put in 5 ones or num bad ones to represent the remaining trump. And then everything else is going to be a 0. So this is similar to what we did with the kings and the queens, where the king was a 10 and the queen was a 1. I don't need the whole deck. And so what I'm going to do is I'm going to have, if num bad equals 5, I'll have 5 1s and then 21 zeros. And now what I do is I'm going to keep track of how many times I have a bad split where all the trump are in one hand. I'm going to do num iteration times. And then what I'm going to do is I'm going to take a random sample of 13 cards from the 26. And I'm going to check and see if the sum of the cards in the hand that I just chose has remained as 0 when I divide by num bad. So again, if num bad is 5, I'm going to check and see, is it a multiple of 5? And if it is, then I'm going to say I have a bad split. And I'll increment the number of bad splits by 1. If I don't, then I don't have a bad split, and I don't increment. And the oh shit moment I had, that's a technical term, as I was preparing for class today, was realizing, oh no, there's two ways that the sum of the values in my hand could be a multiple of 5. What are the two ways it could be a multiple of 5? 0 or 5. I could have none of the cards in my hand, or I could have all of them. But when I do the experiment, when I did it a million times, the observed was 3.942%. When I did it 10 million times, and it took about 3 minutes, it was 3.913%, which is, I think, pretty close to the 3.91%. So if I've made a mistake, it's got to be an extremely small mistake. I probably haven't made a mistake if it's this good. But there's two ways it could be 0 or 5. Why am I okay? Good. If one person has 0, the other has 5. So I just care, does somebody have 5, the missing 5 trump? What I could do is I could check both hands and see, does either hand have 5? Or I could check and see, does one hand have either 0 or 5? If it has 5, I'm done. If it has 0, I'm done because the other one has to. And so again, you can sometimes be very efficient. You can tailor the code for a very specific problem. For those of you who code, I have done a cardinal sin in what I have done here. What is the cardinal sin I have done? Anybody who codes does this, but you should never do this.
No.
Yes. Right? I'll put this in red. -3, no comments. Right? You should never have code without comments. You'll forget things. Like I forgot this morning, oh my God, did I make a mistake? And then I looked at the code and I went through again. No. I'm fine because it's either 0 or perfect. Okay, everything's fine. It's also good to get a sense of how things scale. We increased by a factor of 10. It went over by a little bit more than a factor of 10. That's pretty reasonable because it's just doing the same simple calculation every single time. I'm not creating a huge array or list where I'm storing things and accessing it. This is a code that should be very scalable. If I wanted to do it 100 million times, this took about 3 minutes. I would expect maybe somewhere between half an hour and an hour. So it really would not be that hard to crank this up. You want to get a sense of how long it will take you to do things. There's a great problem in mathematics where we don't know the answer for 5 or 6. And the great Erdős said, if an alien war fleet shows up and wants the answer for 5 and will give us 1 year, we devote all of our resources to this problem. If they want the answer for 6, we fight. Just in terms of, we know 3, I can prove 3 to you in like 3 minutes. It's trivial. 4, it's a little bit more work. And just very quickly, the problem becomes so many possibilities. You want to get a sense of how things scale. You want to get a sense of how far can I go? And one of the great things about simulation is it's a great way to get a sense of what's out there, but it's not a proof. It is possible that the answer is 6%. And we just got incredibly unlucky with our simulations. This is one of the reasons why we will prove things like the central limit theorem, to just quantify just how unlucky would we have to be for the answer to be 6% and do 10 million simulations and have something around 3.9%. I will win the lottery several times over while rooting for the New York Yankees before that happens, okay? It is not something to worry about. Okay, any question on the coding? So I strongly urge you to be able to write some code like this. I've done it in Mathematica. If there's other environments you like, I urge you to just write some simple code, try to get this to work, see how long it takes. All right. How many of you can name at least 5 ABBA songs? If you've seen the movie Mamma Mia, that helps, although I don't know if people are willing to admit to that. All right. Wonderful group. So each here is an interesting question. This is in the book. Each person is equally likely to be chosen from a group of 4. And so being a child of the 70s, I defaulted to ABBA. are the two the same? Each person is equally likely to be chosen from a group of 4, or choose any group of 2 people. All groups are equally likely to be chosen. Are those two equivalent? They are not equivalent. So, in the book, we talk about how the fact that in ABBA, there were 2 marriages and then 2 divorces. What is a reasonable assumption to make about 2 people who are divorced when you're trying to form a group of 2 people? They really don't want to get back, right? And for a while, ABBA would not talk precisely because of this. So we have 4 people. Let's name them A1, A2, B1, B2. Assume A1, B1 do not want to be together. And then A2, B2 do not want to be together. How many groups of 2 people are there? If I have 4 people, how many ways can I choose a group of 2? 4 choose 2. So this 4 choose 2 equals 6 groups of 2. So I could have A1, A2, A1, B1, A1, B2. I'm trying to go in a very nice order so I don't miss anything. I'm looking at all groups starting off with A1 into the group. Now I've handled all the groups with A1. Now let's look at, I don't have A1, so I could have A2, B1, A2, B2, A2, oh, sorry. And now I've got all the groups with A1 and A2, so I'm left with just B1, B2. But we're going to eliminate the group A1, B1 and the group A2, B2. So when I look at it like this, there are 4 groups of 2. How often is A1 in one of these 4 groups? So how often is A1 chosen? Half the time. So notice that each person is chosen half the time. So these are not equivalent statements. There's some nice applications of this if you've seen any error detecting, error correcting codes. This idea of this difference between the 2 comes into play in something like that, which allows computers to very efficiently correct errors. Okay. So let's talk a little bit about some probabilities. I want to roll 2 fair die. So I'm going to assume everybody knows the standard die. We're not going to do Dungeons and Dragons die right now. 6 sides, 1, 2, 3, 4, 5, 6, with the numbers 1, 2, 3, 4, 5, 6. And we will assume each side shows on the top 1/6 of the time. What is the probability if I roll 2 die independently that I get an 11? So how many outcomes can I have if I roll 2 die? 36. So if you want, you can assume first die, second die, left die, right die, blue die, red die. So there are 36 outcomes. Of those 36 outcomes, how many of them will give you an 11? 2. 6 and a 5, 5 and a 6. So we have 2 36ths, which is, of course, just 1/18. But it's better to initially write it as 2 36 to show you where it's coming from. How about having a sum of 7?
There's 6 ways, so 636.
6. And how did you get that so quickly?
Well, I played.
Ah.
And I just kind of know that, but also like 1, 6, 2, 4, 3. 4.
Yep. So one way to extract what you're saying is, does it matter what the first die is? No. No matter what the first die is, one and only one number of the second die will give you a 7. So there's something special about a sum of 7. What if I tell you the first die is a 3 and the sum is an 11? Yeah, that's not going to happen with a standard die. That probability is going to be 0. What about the first die is a 3 and the sum is a 7? What's the probability now? It's 1/6. So notice that the event that the sum is a 7, have I given you any information about the probability of that happening if I tell you the first die is a 3? Does that give you any information about the sum being a 7 if I tell you the first die is a 3? Okay, what information have I given you?
Like the probabilities haven't changed, but presumably,
So the probabilities haven't changed.
but you have to have gotten information because if the first time was a 1, then like, oh, I guess that.
I'm not asking you how the 7 was obtained. So I might care how the 7 was obtained. I don't. I just care, was a 7 obtained? So if I tell you that the first die is a 3, do you have any additional information about the sum being a 7 than if I don't tell you that the first die was a 3? No. No information was conveyed. However, the other one, if I tell you the first die is a 3, you have a lot of information about the sum being 11. Right? What if I told you the first die is a 6? What's the probability you have an 11 now? 1/6, which would be very different than the 1/18th. So as a rough informal description of independence, we would say 2 events are independent if knowledge of one gives you no information of knowledge of another. This is a upper level math stat class. We do not do things informally, but it's fine to just have that in the background as you're thinking about these things. What does it mean for 2 events to be independent? If I tell you information about one, it's not giving me any information about the other. Do you think that this lecture here is going to affect how the Red Sox do later this week in their next baseball game? Do we want to get to the point where, as I lecture, this is going to move air molecules, this could impact the text you guys? We're going to ignore stuff like that, okay? We'll say these events should be independent. If there is some correlation, it is so small we can ignore it. How many of you have ever watched The Price is Right? All right, so at the end of each half, they have a big wheel and you have to spin it, and they have the numbers from 5 to 100 in increments of 5. And whoever gets closest to 100 without going over advances to the final round. Okay? And you can see the wheel before you spin it. And you can spin it once or twice. And there are 3 people who spin. If you go over 100, you're out. So do you want to spin first, second, or third? Third, right? You know, if the first person spins an 85, what do you think they'll do? They'll stop. The second person spins a 75, what do you think they'll do? They'll spin again. You know, if the first person has an 85, they're clearly going to spin again. So the numbers that people get clearly should depend on the people before them. Now, do you think the outcome, if you're spinning the second time, depends on your first spin? Yeah, it depends on how much you push it. And so if you look at where the numbers are, let's say you have a 75 and the person in front of you has an 85. I need to hit, you know, a 10 to tie, a 15, a 20, or a 25. If I don't hit one of those, I'm going to lose. So I might change the amount of force I use to try to hit one of those numbers. So you have to be very careful about, could there be some dependencies? It is much easier in life when things are independent. But there's often some dependencies that, you know, in this situation, I'm going to adjust a little bit how much force I do. For the first spin, you know, a lot of times people try to show off and just show how strong they are and just see how many times they can get it to spin around. Some people try to do exactly the right amount to figure out so that it will come back to the dollar. Okay. So let's try to figure out if there's a nice simple formula for the probability of A given B. So this means probability A slash B is the probability of A given B happens. So we want to try to figure out is there a nice formula for the probability of A given B that depends only on the probability of A and the probability of B? It may be the case that there is no such formula. But again, what I want you to do is I want you to get a feel for how to sniff out formulas. What would be good candidates for A and B? Choose A and B from what? What are good choices? Good. So from A equals B, what else? Empty set? Everything. And there's one other good choice. A equals B complement. Or B equals A complement, depending on which way you want to do it. So let's see if we can figure out what the answer would be in those cases. What would, if we take, if A equals B, then the probability of A given A, what does that equal? It equals 1. So then that would have to be F of probability of A, probability of A. That gives us some information about what this function has to be. Right? If I've got a function of two variables, it's got to reduce to 1 whenever x equals y. So we've already got some information. If B is everything, then what's the probability of A given something happens? It's just the probability of A. And then that would be F of the probability of A and 1. So if I have some function, it would have to reduce to just the probability of A. So if I'm thinking of F as a function of, say, two variables, x and y, it's got to reduce to just x if y equals 1. What if B equals A complement? Then what's the probability that A happens given that the complement of A happens? It's going to be 0. So then that would be F of probability of A. And what's the probability of A complement? Probability B, but what would that be in terms of probability of A? 1 minus the probability of A. So this gives me some feel for what's going on. So if I look at F as a function of x and y, I know that F of x has to be 1. I know F of x1 has to be x. I know F of x1 minus x has to be 0. And this has to hold for any choice of A, any choice of B. So now, is there a good value of x I can use to maybe attack some of these things at the same time? I've got the answer for xx and the answer for x1 minus x. Does this suggest a good choice for x? X is a half. So looking at these two, try x equals 1/2. And so again, what I want you to get out of this is a thought process to attack problems like this. How many of you have ever read a math book where you can follow line by line what is being done, but it is unclear how anybody ever thought to do this? It's where the hell did this idea come from? You might see this in a geometry proof where let's draw this auxiliary line. Well, what made you draw this auxiliary line? This is where AI is going to kick our ass, because AI will just do 20 trillion different things simultaneously. and then just see which one works. We have to try to find a good way to navigate the possibilities. But when we're looking at this, we see f of xx has to be 1, f of x 1 minus x has to be 0. Oh, if we took a situation where x equals 1/2, that's inconsistent. So if we could just find an event that happens with probability 1/2, we're done. Can anybody give me an event that happens with probability 1/2? Yeah, coin flip. Okay, so if the probability of A equals 1/2, if B equals A, then you get the probability of A given B equals 1. If B equals A complement, then you get the probability of A given B equals 0. But both f of 1/2, 1/2. So no such equation or no such formula. And again, we don't need to do this. We have, or we'll get very soon, the formula for conditional probabilities. It's the thought process here. How do we try to come up with, how do we build some intuition? Looking at good events. And again, when we're looking at these formulas, it becomes very reasonable to try x equals 1/2. To try to find an event that happens half the time. Okay. So we need a more complicated formula. So the next thing we can do is let's come up with a function that depends on the probability of A, the probability of B, and the probability of A and B. And then we can go through the games again and try to come up with, are there good choices of A and B? Any thoughts about what the right formula would be? So we know the probability of A given A should be 1. The probability of A given omega should be the probability of A. The probability of A given A complement should be 0. Any thoughts about what might work? And of course, if you remember the formula, you can just say the formula. What do you think?
Maybe something involving multiplied by the probability of A intersection of B, because
Okay. So having the probability of A intersection B in the numerator is good. If B equals A, then that's just the probability of A. If B is A complement, then that's your 0. So that's a really good choice of putting that in the numerator. What would be a good denominator? So we could look at something like this. The probability that A happens given B. So do we want it in the denominator?
just was so this 3% specific probability of A.
Well, we're trying to find a formula for the probability of A given B using the probability of A, probability of B, probability A intersect B.
What about that?
So this is a nice candidate. I'm not saying it's wrong. I'm just asking, do we want the probability to be in the denominator or the numerator? So it seems like this is very reasonable for conditional probability. Notice, if B equals A, we get 1. If B equals A complement, we get 0. If B equals omega, we get the probability of A. This passes all of the conditions you want. There's only one concern you should have. Yeah, what if the probability of B is 0? So this is where you need to know English and you need to be able to read things out loud. So what is the tangent of the arctangent of x? It's x, right? I'm taking the tangent of the angle whose tangent is x. I get x. I want to talk about what is the probability of A happening given that B has happened. What would it mean if the probability of B is 0? B can't happen. So should I really be talking about the probability that A happens given that B happens when B doesn't happen? No. Now notice that the probability of B is 0. What's the probability of A intersect B? It's also 0, and you get 0 over 0, it's undefined good. So if the probability of B equals 0, cannot talk about the probability of A happening given B, as B does not happen. Okay. So again, you always want to be careful. Where can I use something? When my brother and one of his friends were young, we had an old baseball game on the Apple, and they made their own plays. My brother made the ultimate pitcher. He struck everybody out. And his friend made the ultimate hitter, who always got a home run. And they faced off. And the computer just paused for a long period of time. And we thought they had actually crashed the computer. The computer eventually determined what happened when the ultimate hitter faced the ultimate pitcher. Anybody want to guess? Pitcher always strikes everybody out. Hitter always gets a home run. How do you reconcile? Whoever coded this game did one hell of a job. It handled the situation. He gave the hitter a double. Said home run is worth 4 bases, out is worth 0. We'll split the difference. We'll give you a double. Always ask, where should things be defined? So this is a very reasonable formula. Okay. And so, as we said, it passes all the different smell tests. And then, the way we can do it is imagine omega is our space of all possible events. And then B is some subset over here. So I'll put this in red now. So here is B. And now we want to look at some event A. And so we want to look at what is the probability that A happens given that B happens. Well, the part of A that can happen when B happens, what do blue and, I was going to say it makes purple, right? The Williams color. So we have this purple region in here, A intersects B. And the way to view a formula like this is to say, initially we live in the space omega, and we assign probability 1 to the entire space omega. Now we restrict things down to B. And so we rescale the probability up so that the probability of B really gets bumped up to being 1 because B now happens. So this is a really good formula for the conditional probability. Is now we consider B as our entire world, so we have to multiply the probabilities up so that we assign a value of 1 to B. So if B was initially happened 1/3 of the time, we would multiply everything now by a factor of 3. Okay. Does that seem reasonable? Now, there is another way you could rewrite this formula. You could write, I guess I'll do it in purple. The probability of A intersect B is the probability of A given B times the probability of B. What's the advantage of writing it like this? Yes.
It has a more sort of story. I mean, I was just saying that you can interpret it as like the probability of A happening, knowing that it happens, and then how likely is that it happens.
Right, so there's a nice story to this. The probability that A and B happens is the probability that A happens given that B happens, then multiplied by the probability of B. But there's another goodness. It's defined if the probability of B is 0. Now, the other thing is, as soon as you see the probability of A intersect B, if you know that probability, what else do you know? If you know the probability of A intersect B, what else do you know? Probability of B intersect A. How is the probability of A intersect B related to the probability of B intersect A? They're the same. So this is the same as the probability of B intersect A. Well, that's just now the probability of B given A times the probability of A. And so we immediately get the following reformulation. That I can calculate this two different ways. I can first say, let's assume B happens, and then what's the probability A happens given that B happens? Or let's assume A happens, and then what's the probability B happens given A? And these have to be the same. So again, whenever you have formulas, you always want to ask, is the formula symmetric or not? And if it is, what kind of consequences can you extract from that? Okay. So here is one of my favorite problems, and we're going to do it with the expected counts approach. So suppose you go fishing one day and you follow the rules below. You stop fishing as soon as you catch a fish, or it is possible that you've been on the water for 4 hours, you catch nothing, and then you have to come back to go to class. So it's possible that you catch nothing. You could catch one fish, but you're never going to catch more than one fish. Let's also imagine that there's a 40% chance you catch a trout, a 25% chance you catch a bass, and a 35% chance that you don't catch anything. Are those numbers reasonable? And if so, why? Why are they reasonable? They sum to 100. Something happens. You either catch a fish or you don't. So the only thing that I can check here is, yeah, it sums to 100. I have no idea if it should be as high as 40%, 25%, 35%, but they at least sum to 100, so it's reasonable. Noticing the percentage sum to 100 and that you never catch more than one fish in a day, imagine now I tell you you caught a fish. Do you think you caught a trout or a bass? Trout. You have a greater chance of catching a trout than catching a bass. Then I could ask, given that you caught a fish, what is the probability that you caught a trout? Okay. And so we can do this using conditional probability. The probability we catch a trout given that we caught a fish. So we have our event A and our event B. What is event A? So A is catch a trout, and B is we catch a fish. This happens to be a problem where it's really easy to calculate the probability we caught a fish. It's just 45% plus 25%, or was it 35%? 25, and okay. 40% plus 25 is 65%. And so it's just 0.40 probability we catch a trout divided by the probability we catch a fish, which is 0.65. The expected count approach I really like is you start off with some number of days that you're going to go fishing. You choose a number that has wonderful divisibility properties. Notice that I have things like 25%, 40%, 35%. I could probably get away with doing 100 days. I'll be safe and I'll do 1,000 days, just in case I made a small mistake in divisibility and whatnot. And so now, 400 of the 1,000 days, I catch a trout. 250 of the days, I catch a bass, and 350 days, I do nothing. So now I notice that there are 650 times when I caught something. And of those 650 times, 400 times, there was a trout. And so now I can calculate that the probability I caught a trout, given that I caught a fish, is I look at all the days when there was a fish caught, there are 650 such days. 400 of those days I caught a trout, so it's just 400 over 650. I could have done it with 100 days. I just chose something where I would know that I would be safe and I would have nice integer amounts. Would it have been okay if I had pretended it was 37 days? Yeah, I would have had strange fractional amounts and whatnot. It's much cleaner to do something like this. And this is the expected counts approach. It's just go through and make a tree. Okay, so your conditional probability, independence, and Bayes theorem. So if I give you two events, A and B, and their complements A complement and B complement, here are the possibilities. I could have A and B. I could have A complement and B. I could have A and B complement, or I could have A complement and B complement. And so the conditional probability is, let B be an event such that the probability of B is greater than 0, and the conditional probability of A given B is what we've been doing all the time. It's the probability of A and B divided by the probability of B. And we are restricting ourselves to cases where the probability of B is greater than 0 when we're doing these conversations. We're not going to talk about conditional probabilities when one of the events doesn't happen. Now, unfortunately, when you're doing things ahead of time, you may not know whether or not something happens. If you write the probability of A intersects B, that's very safe. Then even if the probability is 0, that is still going to be reasonable. You've hopefully heard the phrase, a picture's worth 1,000 words. You want to learn how to draw good pictures. Unfortunately, you very quickly reach the point where you can no longer draw pictures. Can everybody imagine a one-dimensional space? Can you imagine a two-dimensional space? Three-dimensional space? By induction, you should be able to imagine a four-dimensional space, right? We can play some games. The way we can do something is we can introduce maybe color to represent another dimension when we draw something in three-dimensional space, and the color will represent that fourth component. But it gets hard. Okay? And so at some point, we stop drawing the pictures and we just work formally and we just use good notation. We'll work with tuples of numbers or something like that. Here, anybody know what these are called? Venn diagrams. Okay, so this is a good Venn diagram with three events. Could you do a Venn diagram like this in the plane with, say, 17 events? No. Okay. And so here we have three events, A1, A2, A3, and we look at, here's all the times when A1 and A2 happen, A2 and A3, A1 and A3, and then A1 and A2 and A3. And if we want to calculate what is the probability that A1 or A2 or A3 happens, this is essentially the inclusion-exclusion principle. If the events were disjoint, then the probability that at least one happens is just the sum of the probabilities that any of them happen. It'd be the probability of A plus the probability of B plus the probability of C. But what you notice in this beautiful diagram is the yellow regions are doubly counted. The A1 intersect A2 is counted once because it lives inside the probability of A1, and once because it's part of A2. So that's why when we're trying to calculate the probability of the union, that's why we have this subtraction here of those three terms, because they've been double counted. Unfortunately, now look at the blue in the very middle. It's counted 3 times from A1, A2, A3, but then we removed it 3 times from the intersections. So we have to add it back. And that's why we have the third one over there. So this is essentially what inclusion-exclusion is. We need to make sure at the end of the day, everything is counted once and only once. And the way you should view this is certain events are easy to calculate. Let's calculate those ones. I would much rather do a lot of easy problems than one hard problem. Okay, so we will see some examples of some wonderful problems of trying to calculate probabilities of certain hands of cards or deals of cards. And if you break them up the right way, it's very straightforward. If you break it up the wrong way, you're going to go crazy. And so always reduce things to a lot of easy problems that you can then do. The other piece of advice I always want to give you is go back, once you've done something, go back to a lower dimension and see, does that work here? Well, what if we go back to the probability of A1 union A2? This is still the inclusion exclusion. And so here, this region over here, that would be our yellow region, and that would be the subtraction. And so we would have counted it twice, once from A1, once from A2. We have to subtract it once. So the formula we've seen before for the probability of the union is not so bad. What this should tell you is, in some sense, if I can do unions, I can do intersections. If I can do intersections, I can do unions. I have a way to go back and forth. Whichever one is easier, that's the one I'll do, and then I'll use the formula to get the other one. So I don't care which one is easier. As long as one of them is easy, I'll do that. And so this is the inclusion exclusion formula in its full glory. Okay? I'm going to be very quiet in 389 today. So the union of the AIs, and here we're using a little bit of notation. So we're denoting the number of elements of a set by taking the absolute value. So it's basically the cardinality, it's the number of elements. If you want to, you could also replace these with probabilities. So the number of elements in the union, it's the number of elements in each individual set. Then you have to subtract all the double counting. But then you have to add back all the triple counting. Then you have to subtract the quadruple counting. And you keep alternating, and that's why you get the minus signs. If you are very lucky and all the sets have the same cardinality, then I can replace things a little bit. And we'll see that in a moment. But I guess right here, if all of these sets AI had the same cardinality, this would just be n times the cardinality of A1. If all of these sets AIJ had the same cardinality, it would just be the number of such elements times the cardinality of that set. So let's think about what's going on. How many ways are there to choose two indices I and j that are distinct between 1 and n? And choose 2. This n choose 1 ways to choose 1 index, n choose 2 ways to choose 2 indexes. I want 3 indices that are all different. Because when I'm doing this inclusion exclusion, I don't take the set A1 and A1 twice. I take A1 and A2, or A1 and A3, or A2 and A3. So I have to choose distinct indices. Okay? And so when I look at this, we can prove this by doing some counting. So let's imagine I have some element x in A1 intersect A2 intersect AN. Imagine it's in all of them. I'm going to show that it's counted exactly once on both sides. You could then play the game. What if it's not, it's an n-1 of them? What if it's an n-2 of them? What if it's an n-3 of them? Well, if it's not in some of the sets, just don't draw those sets. Right? If it's not in A5, then anything that has an intersect with A5 is just going to be empty. And so you can just drop that. So it's enough to assume that my element X is in everything. Because if it's in nothing, then it's just not counted. Is everybody comfortable with that? So let's imagine X is in the intersection. That means it's in everything. So from the first one, from the sum I equals 1 to n of AI, we count it how many times? N, but I don't want to write n, I want to write n choose 1. And then for the sum 1 less than equal to I less than j less than equal to n of AI intersect AJ, we count it how many times? N choose 2. And so we get n choose 1 minus n choose 2 plus n choose 3 minus n choose 4 dot 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 dot. And then the last term is going to be plus -1 to the n-1 n choose n. Whenever you have a formula like this, it's always a little bit of a pain as to what is the last one. Is it a +1? Is it a -1? How can I quickly tell if I'm correct by it's -1 to the n minus 1? How can you tell that I've made a mistake or have not made a mistake? Good. Right. We know when the bottom is an even number, it has a minus sign. When the bottom is an odd number, it has a plus sign. It's alternating. So if n is even, I should have a minus sign. Good. N minus 1, if n is even, will be odd, so I will have a minus sign. So by checking this special case, I can convince myself that I've got it right. Okay. If you look at this, does this look a little bit like the binomial theorem? But isn't it missing something? What is it missing?
Powers.
It is. So one thing that's missing, it actually has the powers. Because you can view the powers as -1. But there's something that it's missing. I've got n choose 1, I've got n choose 2, I've got n choose 3, all the way up to n choose n. What am I missing? You're a computer scientist and you don't get this. You're,
0.
yeah, right? Computer scientists start counting at 0. And my son learned very quickly, because his dad was a mathematician, if I told him you can do something 3 more times, he would start counting with 0. No, Daddy, that was 0. And he knew I was so proud of him that sure, you can do it 4 times. Right? This is missing an n choose 0. Should it be a plus n choose 0 or minus n choose 0? It should be a minus. Am I allowed to just put in a minus n choose 0? I can't just put in a minus n choose 0, but what can I do? I can put, if I put in a minus n choose 0, what do I have to balance it with? Yeah, I'll put in a plus n choose 0. If I do that, then it's okay. Right? And now, where does this minus n choose 0 want to go? It wants to go to the very front. So this is really the same as, and of course, n choose 0 is just 1, right? This is really the same as 1 minus, and then it's going to be n choose 0. I'm going to pull out a minus n from everything, plus n choose, I'm sorry, minus n choose 1, plus n choose 2, minus n choose 3, plus ... plus -1 to the n choose n, because I pulled out a minus sign. And I can view that as 1 minus, and then this is going to just be 1 minus 1 to the n. When you use the binomial theorem to expand that out, that's what we get. What's 1 minus 1 to the nth power? It's just 0. So notice we get 1. So if x is included in all of the a's, its contribution from the right-hand side is 1. We counted the element. So this is the proof of inclusion and conclusion. At the end of the day, we counted it. And we only counted it once. And again, if it wasn't in all of them, if it was in all but the last one, then just anything that had an an would vanish and you would do a very similar argument. Or you could do it directly. This is where I'm resisting my temptation to be the pure mathematician and do everything in excruciating detail and just say, hopefully this is good enough. If not, happy to talk to you. TAs are happy to talk to you. But this hopefully gives you an idea of how it's done. Okay. This is just going out and just putting in all the binomial coefficients. And if we're lucky that all of these have the same probabilities, then it simplifies. And there are a lot of events where they will all have the same probability. And we will see that. I don't know if we'll get to derangements today. Probably not. We'll see. So a big caveat for independence of 3 or more events is it's not enough to say that the probability of A intersect B intersect C is the probability of A times the probability of B times the probability of C. For 3 events to be independent, it's not enough that the probability of the intersection is the product of the probabilities. So you can look at the examples in the book and go through some, interesting cases. But for 3 events to be independent, you need the product of the intersection, the probability of the intersection is the product of the probabilities, as well as any 2 of them are independent. If you had 4 events, for the 4 events to be independent, then not only must the probability of the intersection of the 4 be the product of the probabilities, but any 3 of them must be independent, which then by definition gives you any 2 of them must be independent. Okay. So we talked a little bit about this already, the general multiplication rule. The probability of B given A times the probability of A is the probability of A given B times the probability of B. And this is coming from the fact that both of these equal what? They're both just A intersects B, the probability of A intersects B. So by rewriting that, we get the probability of A given B is the probability of B given A times the probability of A over the probability of B. I'm not going to ask you to prove it. I'm not going to ask you to use it. I'm just asking, do you remember the law of sines from trigonometry or geometry? It's like the sine of A over side A equals the sine of B over side B. And they give you these triangles. And they give you 3 of the 4 quantities. And they say, use the law of sines to figure out the 4. That's basically what we're doing here, except for stuff that actually matters, right? Nobody really cares about that 4th quantity from the triangle, I'm sorry. But these probabilities we care about. And so the hope is that we often want to know either the probability of A given B or the probability of B given A. And the hope is if we know 3 out of 4, we know the 4th. This is why Bayes' theorem is so important. What if we only know 2 out of the 4? Yeah, but no, we need to know 3 out of 4. So as long as you know 3 out of 4, then we're fine. This is one of the most important problems I think you will see in your college career. I cannot stress enough how important this is. Okay. Out of curiosity, how many of you have seen this problem before this class? Oh, okay, yeah, it's like before this class. So this is one of the most important problems. So nationwide, tuberculosis affects 1 in every 15,000 people. Suppose there's a TB scare in your town, and for simplicity, assume that the rate of incidence of TB is the same as the national average. Again, always be clear what your assumptions are. Just to be safe, you go to a doctor and get tested for the disease. The doctor tells you the test has a 1% false positive rate. What does that mean? That means that every time 100 healthy people go through and take the test, we expect 1 of them to test positive, even though they're healthy. So out of every 100 tests of healthy people, 1 will be reported as being sick. The doctor reveals that the test has a 0.1% false negative rate. So what that means is for every 1,000 sick people that go through, 1 person will be sick. Okay, only 1 will test negative. Okay. Which do you think is worse, telling a healthy person that they're sick or telling a sick person that they're healthy? Telling this, why is it worse to tell a sick person that they're healthy?
Because there's an impact happening to them that's negative they don't know about versus
Good.
they were.
Good. So if you're sick and you're told that you're healthy, you don't get treatment potentially, and that could have catastrophic consequences. What if you tell a healthy person that they're sick and they're not sick? You might have given them treatment that they don't need. So what should you do if you think that you have this illness? Should we just give you the expensive treatment first, which might have bad side effects? What could we do?
like a ladder of diagnostics, you can like have a cheap test. And then you-
Good. So what you typically do is you have a cheap test to try to flag people, and then you might have the more expensive test. I gotta be careful because this is being recorded. What would you do if, let's say the test is a life-threatening illness and you're going to die if you have it? And somebody tests positive. And maybe they don't have it. We're gonna give them another test. Do you tell them you tested positive? Or do you maybe say the test was inconclusive or the test got contaminated? I'm really sorry, we have to test you again. To manage people's expectations. Something to think about as to how do you want to present information. So imagine you are told that you have a positive test. Do you think you have tuberculosis? Or do you think you were one of the healthy people who just happened to test? The key thing is so few people have tuberculosis, it's going to turn out you're more likely to have been healthy. So let's look and see what we know. The probability that you're sick, well, we're told it's 1 over 15,000. What's the probability that it's positive? We can figure that out by bringing it into cases. What's the probability that it's positive given that you're sick? We can figure that out. We can actually figure out all of this stuff. So if we do the calculation, and I've split up on the right into two parts. So here on one side is the probability that you're sick. We'll call that event B, that you're sick, and we'll call B complement that you're not sick. And so the probability that you're positive, well, you're either positive and you were sick, or you're positive and you're healthy. And what are the possibilities for the two cases? What's the probability? Well, these are the only two possibilities. You're either sick or healthy. The probability that you're sick is 1 over 15,000. And so what's the probability you test positive given that you're sick? We told you that the test was right 99.9% of the time in identifying sick people. So it'd be 0.999. Or you might be healthy. What's the probability you're healthy? 14,999 out of 15,000. What's the probability you test positive given that you're healthy? That was only 1 in 100. So the probability that you test positive, I'm saying it's about 0.01. Is it actually 0.01? Yes or no? Is it exactly 0.01? No. This first number here, I basically have 1 times 1 over 15,000. What is 1 times 1 over 15,000 approximately? Which is approximately? Approximately 0. And then the 0.01 times 14,999 over 15,000. 14,999 over 15,000 is approximately 1. So just, I could refine this a little bit, but it's approximately 0.01. So when I put this in, the probability that you're sick, given that you test positive, is only 0.0066. It's less than 0.1%. Should you be worried? No. And if you test positive, you'll be worried, right? But the odds of you being sick, we could also, of course, solve this with the expected counts approach. I love the expected counts approach. Imagine I have 15 million people. 14.999 million are not infected. 1,000 are infected. Of the 14.999 million who are not infected, we can then calculate what percent test negative, what percent test positive. Almost always the test is correct if you are healthy. Only once out of every 100 are you going to have some problems. And so now we can see who are the people who test positive. Well, at the end of the day, these are the people who test positive. If you look at that, only basically 1,000 people who test positive actually have it. 150,000 approximately people who test positive don't have it. So when you look at the expected counts approach like this, it really drives home the fact that if you have a positive test, it is unlikely that you are ill. All right, so the last thing for today is the law of total probability. Is if we have some events B1, B2, B3 that form a partition for the space, so one of them happens and only one of them happens, then the probability that A happens is the probability of A given B times the probability of Bn times the probability of Bn. So we'll do this in more detail in the next class. I don't want to go through this too quickly, but the idea is to take a complicated event and break it up into a lot of simpler disjoint events And then if I can understand each one of them, I can then build things together. All right, so this is a good place to end. Have a good rest of the day.